Assalamualaikum and hi everyone. So today we are from Group Medicine and Drugs. We'll be presenting to all of you about nanotechnology of medicine and drugs in how nanotechnology help repair the body. What is nanotechnology? Nanotechnology is a field of research and innovation concerned with building things, generally materials and devices, on the scale of atoms and molecules. A nanometer is 1 billion of a meter, 10 times the diameter of a hydrogen atom. Next, what can nanotechnology do? Nanotechnology is hailed as having the potential to increase the efficiency of energy consumption, help clean environment, and solve major health problems. It is said to be able to massively increase manufacturing production at significantly reduced costs. Product of nanotechnology will be smaller, cheaper, lighter, yet more functional and require less energy and fewer raw materials to manufacture, claim nanotech advocates. So, how can nanotechnology help to repair the body? Through the development of biomaterials and nanostructures with possible clinic effects, nanotechnologies have been interested in regenerative medicine. Their goal is to build systems that can replicate, improve, or even establish strategies for in vivo tissue repair. In reality, significant developments have already been made in the field of tissue engineering, cell therapy, and cell delivery in the last decade. We will look into the latest research development in this analysis and explore whether cell and tissue repair equipment is possibility. This analysis focuses on the application of nanotechnology in tissue engineering research and highlight recent development in the application of nano-engineered scaffolds designed to substitute or repair the skin, cartilage, bone, nerve, tissue, and also cardiac that are followed. Electrospinning. Electrospinning is a method to produce ultrafine fibers by charging and ejecting a polymer melt or solution through a spinneret under a high voltage electric field and to solidify or coagulate it to form a filament. The working principle of electrospinning. There is three main components we need to do this electrospinning process. The first one is high voltage power supply. The second one, a polymer solution reservoir with or without a flow control pump, and the last one is a metal collecting screen. The polymetric solution is kept in a reservoir and connected to a power supply to establish a charged polymer jet. High voltage power supply will charge a polymer solution, and then the polymer solution will come out the result at the metal collecting screen.
The primary function of the skin is to act as a barrier. Consequently, any related problems such as burns, chronic wounds, ulcers, or accidents can cause serious health complications. Skin are comprised of two layers, dermis and epidermis. The skin are easily damaged, thus the need of research for skin regeneration. Skin tissues engineering is based in the creation of scaffolds that must share the following minimal characteristics. The first one is biocompatibility. The second one is support for cell attachment and proliferation, and the final one is to imitate the extracellular matrix (ECM) as closely as possible. Lithotroph-spun nanofibrous scaffolds have been created to mimic the three-dimensional fiber network of the collagen fiber structure and has been proven to support cell addition, proliferation, and differentiation, mimicking the fibrous architecture of the extracellular matrix. The development of nanotechnology has also allowed the creation of nanoparticles that act as a vehicle and carrier of biological factors that induce skin regeneration. Cartilage injuries lead to joint pain and loss of function. Hyaluron cartilage has a very low self-repair potential due to its intrinsic properties. A new approach for the treatment of articular cartilage defect is the use of biocompatible scaffold. ECM of cartilage tissue is comprised of collagen and proteoglycans, which are nanometers in scale. Thus, scaffold for cartilage tissue engineering have to be accomplished on the nanoscale to achieve similar mechanical and physical properties to native tissue. To better recapitulate the ECM environment for cartilage tissue engineering, researchers have introduced several biological signals, including chondroitin sulfate, hyaluronic acid, and collagen into tissue-engineered scaffolds. Another strategy for catalyst tissue engineering is to induce chondrogenic differentiation of adult stem cells by the delivery of growth factor included in nanoparticles that are embedded into the scaffolds.
Okay, now I will explain about cell repair and bone reconstruction and nerve regeneration. Okay, first I will start with applying nanotechnology to bone reconstruction. In this picture, we can see the microstructure and nanostructure of bone and bone regeneration. A, B, C, D, E, F, G, H, and I is the nanostructure for bone and bone regeneration. Okay, nanotechnology is bone healing is an emerging field which in orthopedic surgery. There is requirement for bone healing technologies which are biochemical and structurally similar to bone. Nanotechnology is a potential solution as the arrangement of bone including nanoscopic collagen fiber and hydrostatic. As a result of this limitation, the engineer of new bone to replace the damaged bone based on synthetic biomaterial such as metals, polymers, porous ceramic, hydrostatic, collagen sponge, or hydrogel. Energy transfer is widely used to make sure support from nanoparticle and biomaterial including synthetic organic polymer such as PCl, PLJA, PLLA, and polymer such as natural chitosan and seal fibrous. Material used for bone remodeling including biological compatible PLLA polymer which has the advantage of its highest biodegradability. PLLA has been approved by the Food and Drug Administration for use in bone graft surgery. Next, I will explain about nanotechnology for nerve regeneration. Incomplete recovery from peripheral nerve injury can have many negative consequences such as numbness, decreased sensor or motor function. The main treatment for goal is surgery, which require a autologous nerve transplant. However, there are many complications associated with this method. For example, donor nerve function, limited access to donor tissue, and neuritis may occur. Biocomposite nanofibrous scaffold made from a blend of synthetic and natural polymer provide a solid foundation for tissue building and are used as nerve conductor, eliminating the need for autologous neuron. A nanocomposite is multi-phase compact material where the dimension of the one of its phase is in the size range of 1 until 100 nanometer. This nanoparticle can be used as the link between the molecule of different composite polymer due to their advantageous size and directly affect nanocomposite thermal, mechanical, electrical, catalytic, optical, and chemical properties. POSS nanoparticles are one of the most promising nanomaterials for medical application, consisting of a distinctive nanocage structure comprising an inner inorganic framework of silicon and oxygen atom and an outer shell of organic functional group. Nanofibrous scaffold also offer great potential in the field of neurous tissue engineering. That's all from me. I will pass to my friend to continue.
Now, let's talk about nanotechnology for cardiac tissue regeneration. In this modern era of advanced technology, cell injection directly into the heart has proven to revolutionize the treatment of heart disease. This can be seen as some clinical trials have been conducted injecting autologous stem cells derived from the bone marrow, and as a result, there are some improvement in the left ventricular ejection fraction and concomitant increase in myocardial perfusion that is also have been proven. Nano-engineered heart valves are also a promising approach to overcome the limitation of conventional heart valve prostheses. These valves have been tested in animal models and it shows excellent tissue remodeling. As an example, fibrin scaffold in combination with arterial-derived cells were inserted in a sheep model, and after the duration of 3 months, the fibrin scaffold was replaced by new tissue containing meshed collagen along with functional blood vessels. This is a good example on why nano-engineered heart valve is needed to produce good results. It is important to advance further in bioengineering that can create cardiac tissue. Advances in nanotechnology have allowed the researchers to fabricate scaffolds with the aim to mimic or imitate the natural cell environment with the physical properties that influence the physiological behavior of the tissue. As a result, they have made tissue engineering of heart valves or injection of nanomaterials that can improve the function of faulty heart valves. That is also one of the emerging alternatives that improve current modes of therapy in valvular heart surgery. Last but not least is about clinical trials. It is known that a clinical trial is conducted through 5 consecutive phases. The first one is exploratory study involving very limited human exposure to the drug with no therapeutic or diagnostic goals. The next phase involves studies that are usually conducted with healthy volunteers and that emphasize safety. After that, studies that gather preliminary data on effectiveness. The fourth phase is studies that gather more information about safety and effectiveness by studying different populations and different dosages and by using the drug in combination with other drug or medical device. Last but not least, the last phase, studies occurring after FDA has approved a drug or medical devices for marketing. These studies gather additional information about safety, efficacy, or optimal use. In conclusion, with the help of nanotechnology, clinical trials can be a lot more helpful in discovering new treatment for a disease.
Conclusion: the nanotechnology field is advancing fast. This interdisciplinary approach is leading to a rapid expansion and advancement in the production of tissue engineering biomimetic scaffolds. In the goal of improving the treatment of many diseases, nanotechnologists, cell biologists, and medical doctors have started to walk the road towards personalized medicine. That's all from us. Thank you.